have acetylcholine and norepinephrine. Then you have a number of other neurotransmitters in your central nervous system, such as, in addition to the acetylcholine and epinephrine, you have things such as dopamine, glutamine. Okay. However, a more useful way of classifying your neurotransmitters is in terms of those which are excitatory neurotransmitters, and those which are inhibitory neurotransmitters, and those which are both. Okay? Anyone to give us an example of an excitatory neurotransmitter? Meaning it's a neurotransmitter that will produce a excitatory postsynaptic potential. Okay. Anyone? Give us? Yes?
Acetylcholine.
Acetylcholine, isn't it? Norepinephrine. Those are excitatory neurotransmitters. What about inhibitory neurotransmitters? GABA, isn't it? Well, do you know what GABA stands for? Gamma aminobutyric acid. Okay, the most famous inhibitory neurotransmitter that we will come across. Okay, and then there are those neurotransmitters which may have either function. Okay, mixed. So we will focus on cholinergic synapses today. Okay, because remember, in as much as we are talking about synapse physiology, what we are really focusing on is neuromuscular junction physiology. And the neuromuscular junction is a cholinergic synapse. When we say cholinergic synapse, what I mean is that it is a chemical synapse whose neurotransmitter is acetylcholine. So we are saying cholinergic. Right. So this is how a cholinergic synapse looks like. So you see, there's this, you can't see my pointer. So there's this here, right? This is your axon terminal, right? This is your synaptic cleft, and this is your postsynaptic cell membrane. Now, when we talk about neuromuscular junction physiology, you need to understand how this neurotransmitter is formed in the presynaptic axon terminal. So you see you have acetyl-CoA, which is combined with this substrate called choline, and the enzyme that catalyzes this is acetylcholine synthetase. Okay, in the presence of ATP, you have the formation of acetylcholine, which is then packed into synaptic vesicles. Okay, and these synaptic vesicles are the ones that are stored in your axon terminal. And when a trigger arises and this axon terminal is activated, you will see exocytosis of this acetylcholine into your synaptic cleft. Okay? This acetylcholine will then work on your acetylcholine receptors on the postsynaptic membrane. Okay? They will form excitatory postsynaptic potentials. Remember, because acetylcholine is an excitatory neurotransmitter, so they will form an EPSP. Right? However, the acetylcholine doesn't persist in your synaptic cleft for too long. It is quickly degraded into acetate and choline by this enzyme called acetylcholine esterase. So it's hydrolyzed. Okay? The choline is again taken up into the presynaptic axon terminal and then is again resynthesized by this enzyme called choline acetyltransferase. So that's how the process occurs. Now, when we talk about cholinergic receptors, it's very important for us to know which ones we are talking about. Okay? They can broadly be classified into nicotinic and muscarinic receptors. What we are saying is that throughout the peripheral and central nervous system, as well as the neuromuscular junction, there are only two general types of receptors which will respond to acetylcholine. Synapses which will respond to acetylcholine. Those that are nicotinic, meaning they have a nicotinic receptor, and those that are muscarinic. I don't want you to, dwell much on that. Just know that the neuromuscular junction is a nicotinic type of receptor. And here is where we are going to be talking about. However, this physiology essentially applies to all of these. Okay? The only difference is what will happen after this synapse works. Okay? Which will be the difference. Right? And what we are going to talk about is what happens at the junction. And what happens after this junction with regards to a neuromuscular junction, you have already talked about, right? And what happens is muscle physiology. Understood? Right. So, zooming into a neuromuscular junction. Let's see if I have a better picture. Okay, yeah. So this is where we are now. We are looking at the nicotinic M type, right? The neuromuscular junction receptor. Okay? And you can see that this is where a nerve that is ending on a skeletal muscle fiber is going to trigger this muscle fiber to develop its action potential. When we zoom in, this is what we see. Now, remember that you've now decided to make a movement, okay? So your central nervous system sends a signal through the nerve going to that particular muscle, an action potential is generated, isn't it? This action potential travels along the axon going to the nerve, okay? And it reaches the nerve that is innervating this skeletal muscle fiber, okay? What's going to happen? Remember, the action potential is propagated using what type of channels? The voltage-gated sodium channels, right? Which are producing your depolarization of the axon terminal. Okay. When it reaches the axon terminal, there's a slight change that occurs in the type of channels that are present. There are voltage-gated calcium channels. Okay? So, what will happen is that this action potential is propagated to the axon terminal by voltage-gated sodium channels. When the action potential reaches the axon terminal, it depolarizes your voltage-gated calcium channel, right, which opens them, okay? The opening of your voltage-gated calcium channels leads to a calcium influx, okay? This calcium influx will then work on your synaptic vesicles, which store the acetylcholine, to allow it to dock on the presynaptic membrane. Remember, you know what is docking, right? Let's say you have you know what a ship harbor is, where there are a lot of ships. Okay, remember, a ship, when it arrives to the harbor, it must dock, right? It must, throw down that thing, that metal thing, and then it docks at the harbor. And that's the same thing that happens. Now, that docking will not take place in the absence of calcium. So calcium is essential. And calcium only will come in when your voltage-gated calcium channels will open. So it docks, it primes itself in order to prepare for exocytosis. And finally, it undergoes exocytosis. And remember, exocytosis is an active process requiring the presence of ATP. So acetylcholine is then released into the synaptic cleft. Okay? And that's what will happen. Now, okay, so this is again just showing you endocytosis and exocytosis. Okay? So there's targeting and docking, which is facilitated by the presence of calcium, priming of the synaptic membrane to fuse with the priming of the synaptic vesicles membrane to fuse with the presynaptic membrane, and then leading to exocytosis of acetylcholine. Okay? Right. Hey, let's do this picture. Let's do a better one. Okay, so you see, now we've said that your calcium is, acetylcholine is released into the synaptic cleft, right? So it will then go and bind your nicotinic M-type receptor, right? Which are the receptors which are present at your neuromuscular junction, right? And these are present on the motor end plate, right? Which is that section of the postsynaptic membrane of the muscle. So at the motor end plate, you have these nicotinic M-type of receptors. When acetylcholine binds to these receptors, these again are ligand-gated sodium channels. Okay? They are ligand-gated what? Sodium channels. What they will do is that they will facilitate the entry of sodium. So there will be a sodium influx. There will be a minor potassium efflux, but the net movement will be of sodium into the cell. Right? And remember, sodium influx will lead to a depolarization. You get my point? Now, what's the difference between this depolarization and the depolarization that will occur? Because remember that even the muscle will have voltage-gated sodium channels, isn't it? That are going to propagate the action potential. that is generated. So this depolarization that occurs at your nicotinic M type of receptor is not an action potential. You get my point? What type of potential is it? It's an EPSP, excitatory postsynaptic potential. Why are we saying it's excitatory? Because it's a depolarizing potential, isn't it? You understand that? So it's a depolarizing potential that is generated at your nicotinic M type of receptors. And why is it generated? Because there is a net influx of sodium after acetylcholine bias. Right. So what's going to happen is that your EPSPs that are generated in the motor end plate will be summated, okay? If the summation of these EPSPs is large enough to cross the threshold to trigger the activation of your voltage-gated sodium channels on the muscle membrane, then an action potential will be generated. Understood? So your EPSPs are what we call graded potentials, isn't it? Do you know the differences between a graded potential and an action potential? Right. So you see, graded potential here, so examples are your EPSPs. If we're talking about, this same thing occurring elsewhere, let's say this is somewhere in the brain, okay, and the neurotransmitter is GABA. Okay, what will be generated? What will be generated? IPSP, isn't it? It's the same physiology. There is still going to be activation of a voltage-gated calcium channel, which will cause docking, priming, exocytosis. But what will be released if it's a GABAergic neuron is GABA, right? GABA will go to the GABA receptor on the postsynaptic membrane, and this time it will cause more potassium efflux than sodium influx, right? So what will be generated is an IPSP. It's the same principle, right? It's just that we are describing this in terms of neuromuscular physiology. And in terms of neuromuscular physiology, the only type of receptor here is a nicotinic receptor, and the neurotransmitter is acetylcholine. So we'll see an EPSP. You get my point? But the principle applies to all synaptic physiology. You understand that, right? So, you have this graded potential that is generated. You see that the graded potential is non-propagating. It is maintained only at the motor end plate. Right? It is not propagated along the rest of the cell membrane of this postsynaptic muscle or neuron. Okay? It is a short distance signal, again, just qualifying that it is non-propagating. It can be only a depolarizing signal, in a case where it's an EPSP, right? Or only a hyperpolarizing signal, right? Unlike an action potential, which will have both a depolarizing phase and a hyperpolarizing phase. Understood? And what will determine whether a graded potential is depolarizing or hyperpolarizing? What will determine that? The neurotransmitter, isn't it? Is it an excitatory neurotransmitter? Then we'll have depolarizing, in which case we'll have EPSP. Is it a inhibitor neurotransmitter? In which case we'll have hyperpolarization and a IPSP. Okay? But in terms of neuromuscular physiology, we just talk about EPSPs, right? Because the only receptor that's there, and the only neurotransmitter that's there is acetylcholine with a nicotinic receptor, right? It does not obey the all or none law, and that's pretty obvious, right? Remember that when we talk about action potentials, a very important principle is the all or none law. Anyone to help us describe the all or none law? What we mean is that the all, no takes, no. Okay. Right, so what we are saying is that this all or none law is saying us that for us to generate an action potential, okay, you need a certain threshold of, to be reached. Below that threshold, it's not that, okay, we only generate half an action potential. Since we just have half the threshold, it doesn't work that way, right? Neither does it work that if we have 10 times the threshold, then we will have 10 times the magnitude of the action potential. That's what we mean. It's either all will form an action potential, or none will form an action potential. You get my point? All or none law. That does not happen with gradient potentials, isn't it? Because they can be summated, right? You can have inhibitory, excitatory. You sum them up, and then they can be cancelled. You get my point? It's not that all EPSPs and IPSPs will generate an action potential, and it's not that none are able to generate an action potential. Okay, that's what we're trying to say. So that leads to the next property, that they can be summated. Okay, EPSPs, and that is the principle at the neuromuscular junction, right? You have numerous EPSPs being generated at these at the nicotinic receptors. If they are all summed and are strong enough to generate an action potential, you will then have an action potential being generated. Understood? So summation can occur. Right. And of course, there is no refractory period when we talk about gradient potentials, whereas refractory period is something that we see in action potential. So, just extending what we're talking about to other types of synapses, okay? So, we are saying that, and this is basically talking about summation, okay? Let us say you have this neuron, the yellow one. You can see the yellow one, right? Let's say that's the postsynaptic neuron, okay? And you have two presynaptic neurons working on this postsynaptic neuron. One presynaptic neuron is excitatory, okay? The other presynaptic neuron is inhibitory. You get my point? So what will determine whether this postsynaptic neuron is going to generate an action potential or not? It's going to be the summation of the excitatory postsynaptic potentials and the inhibitory postsynaptic potentials. Okay? The sum of these two will either lead to a graded potential that will exceed the threshold or reach the threshold needed to generate an action potential, or will not. And that will determine whether this postsynaptic neuron will generate an action potential. You understand? Simple. Okay, again, we're talking about the same thing here. You can see this phase here, the green ones are the EPSPs, the red ones are the IPSPs. So you may have a situation where you have a number of neurons, presynaptic neurons working on a postsynaptic neuron. So this postsynaptic neuron will sum all of the EPSPs and IPSPs, and if this sum reaches the threshold to be generated, you will have the generation of an action potential. If not, you will have no action potential. And that's what we're talking about. And of course, this principle doesn't really apply to neuromuscular physiology, right? Because at the neuromuscular physiology, you simply have one type of receptor. But we're just extending this because we are talking about synaptic physiology as well. Right. So just coming back here, so you have EPSPs that are generated, and if they are strong enough, they will trigger the voltage-gated sodium channels on the muscle membrane to generate an action potential, which will then lead to excitation contraction coupling mechanisms, which you are experts at, and leading to contraction of the muscle. And that is neuromuscular junction physiology. Right. Any questions before we talk about some disorders? Let's be quiet. No. When we talk about all or none principle, we are referring to the fact that a graded potential's ability to generate an action potential. You get my point? That's what we are talking about. So, what we are saying is that an action potential obeys the all or none law. If you reach the threshold, you will generate an action potential. If you do not reach the threshold, you will not generate an action potential. With graded potentials, it's different. They need to be summed up, and the threshold will then determine whether you generate an action potential or not. That's what we're trying to say. Yes. Okay. Yeah.
So action to be directed. There's no situation whereby there cannot be equalization. It just becomes constant from this point.
Yeah, so that's when we talk about tetanus, right? Principle tetanus. But you must have covered that under muscle physiology, right? Now, and you,
The principle applied to animals with the same principle under
I don't get your question, sorry.
the same principle
Uh-huh. That's in muscle physiology. Do you mean it doesn't apply to nerves, to the action force? So you need to understand, when we talk about tetanus, right? We are talking about the summation of contractions generated by the muscle. That doesn't mean the action potentials are adding up. You get my point, huh? What we are adding up is the force of contraction generated. And why this is happening is because we are repetitively stimulating this action, this muscle with a high frequency of action potential. It's not the action potential which is summing up. It's the contraction, the force of contraction being generated by the muscle that is summing up. So you need to understand. That's why the law is that action potentials cannot be summated. You get my point? But muscle contraction can be. I don't know if I've answered your question.
now what causes in the case of tetanus, what causes the continuous stimulation?
Yes. It's the continuous stimulation which increases the force of contraction of the muscle. Yeah. Okay, so let's look at some disorders, but the only thing I want to talk about here is myasthenia gravis. Okay, so myasthenia gravis, you see, it's this disorder of your neuromuscular junction where you see you have your nicotinic M type of receptors, right? And that's where acetylcholine is supposed to bind. Okay, we said they are ligand-gated sodium channels. Now, what happens in myasthenia gravis? It's an autoimmune disorder. Okay, and you have antibodies that are generated against these nicotinic M type of receptors. So where acetylcholine is seated, you have these antibodies that are going to come and sit there and block where acetylcholine can sit. And obviously, how do you think someone with myasthenia gravis will come to you? What will their complaint be? Muscle weakness, isn't it? The inability to generate muscle contractions because of that, right? So they'll come with muscle weakness, okay? So that is myasthenia gravis. There's another condition called Eaton Lambda syndrome where you have antibodies directed against this voltage-gated sodium channel. Okay? Again, presentation will be very similar to myasthenia gravis because remember, the voltage-gated sodium channels are needed for the activation, docking, and priming of these synaptic vesicles, isn't it? So if you have an antibody that is blocking your voltage-gated calcium channel, then your calcium influx will be inhibited. Okay, and that's another disorder. There are others that have been mentioned in the notes, but I just wanted to discuss this because they are relevant to the physiology. Yeah. So yes.
So we have a situation where antibodies are used and upon attaching to the same receptor, they something like an antibody receptor in activating the complement system.
No. These are purely what we call type 2 hypersensitivity reactions. It's simply an antibody that is blocking the function of this receptor. There is not really formation, activation of complement in myasthenia gravis. Yeah. Okay, no questions, and that means group 1 and 2 you have covered everything. So yes, the test. Oh, okay, the question, sorry. Yes.
I came across a list that says that depending on where SCH is combined, it will either cause an IPSC or EPSC. They say that it will bind on the fluorine gated something, and then the fluorine will cause an inhibitory something.
Yeah, so you see, that's why we are saying that the type of gradient potential that is generated on this postsynaptic membrane depends on the neurotransmitter as well as the channel. Now, acetylcholine can bind to certain chlorine-gated channels, in which case, you see, you have a chlorine influx. You get my point? You have a chlorine influx, which will hyperpolarize this cell and hence generate an inhibitory postsynaptic potential. And that is how it occurs. But that does not happen at the neuromuscular junction. It does not happen this happens at other points in the central nervous system. And what we are basically discussing is what happens at the neuromuscular junction, where you have a ligand-gated sodium channels. Understood? Yeah. Yes. Sorry? A muscle cramp. Okay. So cramping of muscles is not related to this. Of course, excessive stimulation at the neuromuscular junction may end up with muscle cramping, but the direct physiology associated with muscle cramping is the buildup of lactic acid in your muscles because of the shift in use from aerobic to anaerobic mechanisms. And when lactic acid builds up, it distorts the normal metabolism of your muscles, and your nerves around, your sensory nerves around the muscle will pick it up as pain, which you perceive as a cramp. Yeah, so it's directly involved to issues of lactic acid and other metabolites accumulating in the muscle. Yeah. Duchenne muscular dystrophy is related to disorders of. Let me see if I think I had a picture that I could use up here. Yeah. So you see, Duchenne's muscular dystrophy, again, is going to be characterized by things such as muscle weakness and the like. However, it's related to the absence of these proteins that will link the integrity of your muscle, of your muscle membrane. Myasthenia gravis is a disorder of your neuromuscular junction. Duchenne's muscular dystrophy is not related to your neuromuscular junction. That's the difference. Guillain-Barré syndrome is a demyelinating disorder. Where did you read about Guillain-Barré syndrome? Guillain-Barré syndrome, what happens in Guillain-Barré syndrome is that you see where you have a spinal cord, right? The spinal cord. That's where this neuron that is coming from. This neuron here, right? This neuron is in the spinal cord, right? That's what we call a lower motor neuron. In Guillain-Barré syndrome, what we see is that there is demyelination of your anterior horns. So the disorder is in the spinal cord. Okay, it's not anywhere here. So if I could put it in a summarized way, Duchenne's muscular dystrophy, a disorder of your proteins of the cell membrane in the muscle, myasthenia gravis, neuromuscular junction, Guillain-Barré syndrome in your spinal cord. Yeah. But again, because you are reading way beyond the context of what you're supposed to know. It's good to know it, but know about how a muscle will contract. Okay? But it's good that you're talking about it. But again, let's calm down. Let's finish up. I think we're approaching the time. Yes. Unfortunately, I can't hear you. Okay. So now let's talk about this all or none law, right? We'll talk about it with regards to action potential. we're saying that a certain threshold needs to be reached in order to generate an action potential. If it's not reached, then no action potential will be generated, right? So that's the none part of it. If we're saying, and the all part of it is saying that any potential, any stimulation at or above the threshold will generate the same type of action potential. And that's what we're saying is the all or none law. Now, with regards to graded potentials, what we are saying is that the all or none law is not really followed. One, because one, the level of neurotransmitter found in the synaptic cleft will determine the level of graded potentials that are generated. It's not that if you have low levels of, it's not that there's a certain threshold that needs to be reached for a graded potential to be generated. You get my point? The amount of stimulation is proportional to the amplitude of the graded potential generated. That's what we're trying to say. I don't know if that helps. But it's not the same thing with action potentials, whereby you have this threshold below which there's no action potential, above which, regardless of the amplitude of stimulation, you will have the same type of action. That's not the case with graded potentials. Okay? Okay, so what we'll do is that let's dismiss, and then if you have any questions, you can just ask them to me right here. Okay, thank you very much. All the best.